Numerical derivatives, integrals, and function handles. Recall that the derivative of a function can be written in the form of dy dx, where dy and dx are infinitesimal changes in y and x respectively. To approximate the derivative, we can calculate delta y over delta x instead. MATLAB provides a function called diff that will take the difference between adjacent elements. So in essence, diff x is equivalent to delta x. You will get an array with one element shorter than the original array. So for example, if my x is a matrix that goes from 1 to 5, calling diff x will return me a matrix with 4 elements, and each element is equals to the difference between adjacent elements. So this one corresponds to 2 minus 1. This one corresponds to 3 minus 2. And this one corresponds to 4 minus 3. And this one corresponds to 5 minus 4, etc. So, to calculate the derivative of a function or some values, what you can do is you can call diff y dot dy diff x to approximate the derivative. So let's try an example. So let's say that I have x which goes from 0 with an increment of 0.1 and stops at 4. Now my y is equals to x squared. Now let me set my x2 to go from 0 with an increment of 0.1 to 3.9. Now to approximate the derivative of y, what I can do is y2 is equal to the diff of y dot divide the diff of x. Now let's try to plot both x and y as well as x2 and y2 and see what they look like. So plot x comma y comma x2 comma y2 and look at our graph. The blue line here is our function y is equal to x squared. And this green line here is its derivative, y is equals to 2x. So this is how we can approximate the derivative of a bunch of points using the diff function. Now let's try this again for the sine function. So my x will go from 0 with the increment of pi over 20. I will stop at 2 pi. My y value simply equal to sine of x. Now my x2 values, which is my values for my derivative, x2 will go from 0 with increment of pi over 20. I will stop at 2 pi minus pi over 20. And y2 is equals to diff of y dot divide diff of x. Now if I were to plot both functions, plot x comma y comma x2 comma y2, and this is our result. So the blue line here is our original sine function. The green line here, the green line here, this is our derivative, cosine of x. So this is how we can approximate the derivative of a function by using the diff function. Numerical integration. We can also use MATLAB to calculate the integral of a function. Recall the trapezoid method for the area under a curve. So if this is my curve here, I can approximate the area under this curve by dividing the curve into segments. So here I can divide the curve into 1, 2, 3, 4 segments. And then for each segment, I will try to place a trapezoid under it, and then I can try to add up the sum. So MATLAB provides a function called traps that approximate the integral of a function by approximating using the trapezoid method. So traps function has the form of traps x comma y. So for example, let's try to approximate the exact value of sine of x dx from 0 to pi. So we know that sine of x dx from 0 to pi is equals to negative cosine of x taken at pi and 0. So if we actually evaluate this, we get 2. So let's try to do this in MATLAB using numerical integration. So first, let me set my x to go from 0 to pi over 100 and stop at pi. My y is simply son of x. Now, all I have to do is simply call the traps method, trapz x comma y, and this will approximate the integral, basically the area under the curve. And here it gives me 1.9998, which is very, very close to the actual answer, which is 2. Now, another way to compute the numerical integral of a function is using the quad function, QUAD, quad. So the quad method takes the form of quad function a comma b, where function is the function handle of the function you're trying to integrate, and a and b indicates the range of the x values. So a and b are basically your limits of integration. So before we can continue with the discussion of quad, we need to learn a little more about function handles. So let's try to create a simple function called square f. Function y is equals to square f of x. Y is equals to x squared. So this is a very simple function that simply returns the square of x. Now, we can create a function handle for square f by entering s equals to as sign and then square f. So what this does is it creates a function handle for the function called square f. Now we may use the function handle as though the square f function itself. So we can simply say s of 10 and give me 100. So s of 10 is equivalent to calling square f of 10. So these two function calls are equivalent. S right now is simply an alias or function handle for square f. Now going back to the quadrature method. To use the quad method, we need to enter the function handle, a and b, which are the limits of the integration. So as an example, let's try to find the integral. Let's try to integrate the function y is equal to x squared from 0 to 1. So the first thing we want to do is actually write the function y equal to x squared, which is basically what our square f function is. So our square f function is simply a function that squares your values. So this is y equal to x squared. Now I want to integrate y equal to x squared from 0 to 1. All I have to do is simply say quad s, which is my function handle, and 0, 1. And this gives me the value of 1/3. So this is how you use the quadrature method. Your first step is to create a function handle, which is s here, for the name of my function. And then simply passing s as a variable to the function quad. It will automatically call it. So this is an alternate method to calculate the integral under a curve or integral of a function.